Hello, this is the luckiest maths teacher in the world, and today we're going to look at sets and Venn diagrams, but we're going to apply this to probability. So first, I'm just going to have a quick recap of the basics of probability. If you think you already know this, just skip ahead in the video a couple of minutes. So, by now, you probably know that probability is a way of quantifying the likelihood of an event. So what we do is we take an event and we give it a number, and that number tells us how likely that event is to occur. So you probably remember that the number we give has to be between 0 and 1. So if the event has a probability up here, it's certain or close to certain. Up around here, it's likely to happen. Of course, in the middle of the scale, 0 to 1 is the number half, or 0.5, and events here have an even chance of occurring. And of course, as we get closer and closer towards 0, the events become more and more unlikely to occur. And if the event does have a probability of 0, it's impossible. There is no way that it can occur, right? So of course, when we're giving the probability of an event, we can't say the probability of occurring is 50-50 or even chance. We have to give it a number. The number indicates whether it's likely or unlikely. But if I say to you, what's the probability of so-and-so happening, you can't respond with the words unlikely or likely. You must give me a number between 0 and 1. So, how do we assign probabilities to events? Well, I know you've done this before. There's a really easy formula that's, I guess, commonsensical to the point where you probably don't need to memorize it. So this is the formula in red, and it says the probability that an event will occur is the number of ways that the event can occur over ns, which is the total number of events in the sample space, or the total number of possible outcomes. So this is a pretty easy formula to use, and you probably would have used it many times without actually realizing you were. So let's say I roll a normal 6-sided die. So I might say, what's the probability that a 2 is rolled? So using this formula, this notation means probability of 2 occurring. The number of ways it can occur is 1, because there's only 1 2 on a normal 6-sided dice, but there are 6 outcomes in total. So if I was interested in the probability that an even number would come up, there are 3 even numbers on the die, so there's 3 ways it can occur. I can get a 2, a 4, or a 6, and again there are 6 outcomes in total. So when we write fractions for probability, we must simplify them. It is okay to write probability as a decimal, so I could just as easily write this as 0.5, okay? So now we're going to look at something a bit more complicated. We're going to look at Venn diagrams and how we can apply probability to those kinds of questions. Now, we're talking about sets. A set is just any collection of objects. It makes sense to think of, say, the set of all Year 9 students or the set of all people who play footy. But of course, because we're applying this to probability, we're interested in sets of events. So the sets we're looking at will be collections of events. A Venn diagram is just a way to visually display 2 different sets of events, and that helps us find probabilities of certain things. So I will now draw a Venn diagram and show you what they look like, but you've probably seen them before. So this is what a Venn diagram looks like. So there's a big rectangle which represents the universe, all possible things. And then we have 2 circles. One of them I'll just call A and one B. So these circles represent sets of events. And we're looking at sometimes events that overlap with each other. So let's say that I'm going to pick a random whole number between and including 1 and 20. So let's say that A is going to be the event that the number I pick is prime, and B is going to be the event that the number I pick is odd. So what I can do is I can write in each set all of the numbers that are true of that set. So if I'm looking at A, so again I'm looking at all the numbers between 1 and 20, or the whole numbers. So prime numbers, we have 2, 3, 5, 7, 9, of course, is not a prime number. So 11, 13, 15, which is of course not a prime number. 17, and 19. So now, if I get rid of the 9 and 15, I have all the prime numbers between 1 and 20. So now, I'll do the same for B. I'll put in all the odd integers. So it's just 1, 3, 5, 7, 9, 11, 13, 15, 17, and 19. So what goes outside the two circles are all the numbers that are in neither set. So these would be the numbers that are neither prime nor odd. The numbers I haven't already written down. So they'd be 4, 6, 8, 10, 12, 14, 16, 18, and because I said less than or equal to 20, I'll include 20. So this big black box represents the universe. In this case, the universe is the set of all numbers, all whole numbers between and including 1 and 20. A and B are just subsets of that. Now, what you probably notice is that this visualization is a little tricky, and it's sort of redundant because what I've done is I've written some numbers in more than one spot. So you can see, for example, the number 3 is in both A and B. So why would I write it twice? Well, instead, what I can do is I can get rid of each of these 3's, and I can just write them in the middle, because this middle space are elements that are in both A and B. Now, I can do that for a few more. I can do that for 5, 7, 11, because these numbers are prime and odd. So I'm going to do that now. So now, the Venn diagram is a lot easier to work with. Each number is represented or written only once. And so we have special names given to each section of the Venn diagram. So this section here, this contains elements, in this case numbers, that are in set A as well as set B. And we call that set A and B, but we write it like this, A with a little sort of N-looking shape. That means at the intersection of A and B, elements that are in A as well as in B. Now, this whole section that I'm shading in now, this whole section here inside the circles is called A union B, or you can read it as A or B. And everything outside of the circles, which is stuff that doesn't lie in A and also doesn't lie in B, that's called not A or B. So this little line there means it's not in. Another way to do that, another way to say that, we could write A or B in brackets and put a little dash there, or we could put a little C there. They all mean the same thing, not. So if I wanted to list the set here A, C, or which is the same as A dash, that means all the elements that are not in A. So that would include the elements, of course, that are not prime. So all the numbers between 1 and 20 that are not prime. So you've got 1, 4, 6, 8, 9, 10, 12, 14, 15, 16, 18, and 20. So we usually use these squiggly brackets to say what's in a set. So that is the set not A, all the elements not in A, right? Now the set A and B, I'll write it a bit bigger for you this time. So the set A and B is the set of all the elements that are in both. So we write it like this, squiggly brackets again to indicate a set, 3, 5, 7, 11, 13, 17, and 19. Okay, so that is the set of all elements in A and B. Now we, of course, can use this to find the probability. So let's say I picked a whole number between 1 and 20 at random. So I could figure out what is the probability that the event is in A and B, or in other words, that the event is both prime and odd. Well, looking at the Venn diagram, that's simple. There are 1, 2, 3, 4, 5, 6, 7 elements that are in both A and B. So the probability, there's 7 ways it can occur, 7 ways I could pick such a number, and there are 20 in total. I can figure out, say, the probability that the number is neither in A nor B. So that, of course, the probability that it's not in A or B, so I'll just put a line up there too. to indicate not. So the probability it's not an A or B, we can just count 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 elements that are neither prime nor odd. So that's 9 over 20. So that would have been a little bit harder if you didn't have the Venn diagram. So the Venn diagram presents the information and makes it a lot easier to see. So now we're just going to do one more type of question involving Venn diagrams. So let's have a go at this question here. In a class of 30, students were asked whether they like football, tennis, or neither. 20 liked football, 8 liked tennis, 9 liked neither. And we're going to find the probability the student liked football but not tennis, and then find the probability a random student selected would like tennis but not football. So this probably doesn't look like it would have anything to do with Venn diagrams, but Venn diagrams are just a way of presenting the information, organizing the information so that the question is easy. So let's first draw up a Venn diagram. Okay, so here is the Venn diagram. So the sets we'll call A and B again. Now, because the question was talking about students like football and students that like tennis, that's what the sets will be. So A will be the set of students that like football, B will be the set of students that like tennis. So the way we do these questions is we first look at how many students like neither. So it says that 9 out of the 30 students liked neither. So we're going to put 9 here. So in the last example of Venn diagrams, we listed all the elements that were in each set. But in Venn diagrams, we can actually just put the number that are in each set or the probability that something is in each set, just to make it easier. So instead of writing out the 9 names of the kids, because that'll take too long, I just put the 9 there to indicate there are 9 students that fall outside the circles that like neither football nor tennis. So then, if 9 like neither, obviously 30 minus 9, 21 students like at least one of football or tennis. So the numbers in here, in the circles, they will add up to 21. The problem is, however, 20 like football and 8 like tennis. That's 28. So that means there's 7 too many. So the only way that this will work is if 7 goes in the middle. There are 7 that liked both. And because there were 8 that liked tennis in total, if I put a 1 here, I can see that 7 plus 1 is 8. So there are 8 inside this circle. 8 students that like tennis. And similarly, I'll put a 13 here so that there are 20 students in this circle. So of course, the reason that the number of students that like football, tennis, and either added up to more than 30 is because some students like both. So once we've put the numbers in, to figure out the answer to the probability questions is easy. So the probability that a person likes football but not tennis. So what we're essentially looking for is the probability that they are in A, like football, but they're not in B. So that's how we write A but not B. So that's the probability we're after here. Another way you can write this is the intersection of A and B complement, or not B. So we can see very clearly from this diagram there are 13 people in the football circle that are not in the tennis circle. So the probability, if I select a student at random, is 13 over 30. There are 13 students I can select, 13 ways I can select such a student, out of 30 in total. So similarly for the proportion or probability that I pick a student who likes tennis but not football, there is only one student who is in the tennis circle but not the football circle. So this is the probability of B, which is the event the student liked tennis, the set of students like tennis, and A complement, B but not A. There's one student who is in the circle B but not in the circle A, so the probability the student selected at random likes tennis but not football is 1 over 30. I hope you've enjoyed this video. This has been the luckiest maths teacher in the world. Have a great day.